All right, so I'm going to finish out discussing the optimization for deep neural nets and talking about different optimizers. So throughout this class, we've been talking about stochastic gradient descent and mini-batch gradient descent. And in SGD, of course, the basic operation is that we take our parameters, so let's call it, for example, W, and then we replace it with W minus some eta, and this eta can change with t, so this is in the tth step, eta t times our gradient of our loss, and let's write it L sub m, capital L sub m, of just W, for example. So this L sub m is the mini-batch risk, right? The average of the mini-batch losses. Empirical risk. I'll just write ER for empirical risk. Now, this is obviously not the only choice we could have made for how we modify the W given a gradient update. So you might have seen in some convex optimization, smooth convex optimization, the use of Newton's method, where instead of a fixed step size, you replace that with the inverse of the Hessian or some surrogate of the Hessian. Now, for convex optimization, that might be a good idea, but there's very simple examples in non-convex optimization, which neural nets are non-convex optimizations. There's very simple examples in non-convex optimization where Newton's method will actually do something quite bad, which will bring you back to what are known as saddle points. So Newton's method actually in some situations does the exact opposite of what you would want. So we won't rely on Newton's method, and those are called second-order methods. Instead, we will rely on, for example, other modifications to SGD, which are intended to deal with specific scenarios that are quite common in deep neural nets. So one of these scenarios is a situation where you might have some descent direction in your objective. So you have your objective, which has some descent direction. Here, I'll try to draw that a bit more clearly. Some descent direction. So this is, for example, the gradient that we would like to move down if we were at this point, but we're not quite at this point. We're off of it. Say here's our initial value. But then if we look in the direction that's orthogonal to this descent direction, then we might have very steep slopes and high curvature. So this can happen, and the reason why you might have very dramatic gradients in certain locations is that in deep neural nets, because you're composing many functions, so for example, if you compose two sigmoids together, you can get very steep gradients. So if you compose, for example, two sigmoids, then this yields something that looks more like a cliff, right? And so this can happen quite a bit, things like gradient cliffs and very dramatic changes in the gradient that you might want to deal with by sort of averaging out the previous gradient steps. And this is especially true because SGD does produce noisy gradients. And this noise in non-convex optimization settings actually can be an asset because this noise can, in a sense, allow you to jump out of local minima. Right? So it could allow you to jump, for example, out of this local minima just because it's a noisy update. Whereas with gradient descent, you would never get out of this local minima if you were at that minimum point, because the local minimum would be a stable point for gradient descent, but not necessarily for SGD. But then this issue of having steep gradients in a specific direction, it can cause issues because if you have a very large gradient, so that's what steep means, if you have a large gradient in terms of its magnitude, then you're going to make a larger step size because your schedule doesn't necessarily adapt to the size of the gradient itself. So there are a couple of ways we deal with issues like this, gradient cliffs, and then other instabilities caused by large gradient norms. One is just gradient clipping, and you see this every once in a while in use, but we'll talk about more dramatic changes. So gradient clipping, you'll see this sometimes, where you replace the gradient, we'll call it G, gets the original gradient, Lm of W, but over the norm times C if the norm of the gradient exceeds some value, exceeds C. If the exceeds C. And then it's just not altered at all otherwise. So this is something that you could do. And it just effectively sets the gradient norm to be no larger than C. So you just set it to be C if it does exceed C. So this is one option for dealing with these gradient cliffs. But let's imagine the following scenario. And this is what I was getting at earlier. Let's imagine the following scenario where you have these are level sets. These are the values of your optimization. Sorry, this is kind of a messy picture. If you were at a point here, then you have a very large magnitude for the gradient, so you would jump quite far over into this direction, and then you would see a very large magnitude in the opposite direction. You would jump back here, and you would spend a lot of your energy just jumping back and forth here. And gradient clipping might not really alleviate this problem because the direction in which you're moving is orthogonal really to the direction in which you want to move. So if we just look at it from top down, then we have some directions where we have a true descent. Here's say the local optima that we would like to get to. And then you have other directions of steep descent, but those will cause us to oscillate in our SGD steps. So one way we can deal with this is to include what's known as a momentum term. And sometimes we call this acceleration, which kind of sounds like a misnomer, but anyway. Acceleration means that we're going to remember past directions. And this is in a momentum term. So how are we going to do this? Well, let's take our current gradient, multiply it by some number alpha. So we have a current gradient from a previous step, and then we multiply it by some number alpha, which is going to be less than 1. So we have alpha is in 0, 1. And then let's subtract off from G some epsilon parameter times the gradient of just our mini batch loss, which I'll just write it out, of yi of f sub theta of xi. Right? So we're doing some sort of a some combination of G, the previous gradient step, and then the gradient for the mini bash, the current mini bash, and we're using this to update G. So the basic idea is that G not only includes the current mini batch gradient, but also all of the previous gradients, but to some lesser degree. Right? And then when we make our update to theta, it just gets theta plus G. Right? Okay. So you can imagine that what this is going to do, it's going to sort of dampen this oscillation a bit. So you get something that would dampen a bit more, because all of these oscillating terms are going to cancel out with one another, right? So that's the basic idea behind acceleration, is that it sort of remembers these past directions. Nesterov had an idea to include, to modify this acceleration term a little bit. So we call it Nestorov's acceleration. So the basic idea here is that the gradient is applied at, so by gradient I mean this gradient here, is taken at theta, but if you see what we do, we add this gradient to some theta plus alpha times G, right? Because we're already committed to making the alpha G be included in our current gradient update, in our current step directional update. And so why don't we just, instead of taking this gradient at theta, take it at this theta plus alpha G. So this is applied to theta plus alpha times G. So instead, let's make the following update. G gets alpha times G minus epsilon times the grad of theta times this 1 over m, sum I equals 1 to m of the loss at yi and f at theta plus alpha G of xi. Right? So we're just going to apply it to the gradient here. Right? So this is the basic idea behind Nestorov's acceleration. And we have both theoretical and experimental evidence that Nesterov acceleration actually can improve things significantly. Okay, so that's another idea. And all of these, let's just step back for a second, all of these simply modify how the gradient update is made, but they all sort of can take the same interface. You calculate gradients at some point, and then those gradient updates modify the theta in some way. But if you have an optimizer, it's going to have to remember the previous gradients to some extent. Okay, so that's another trick that people will use for first order methods. So another idea is quite a bit different, and I won't go into the math for this one, but it's the Adagrad idea. So John Ducci and his co-authors came up with this idea, and it was also incorporated into RMS prop, which is effectively the same idea in a slightly different incarnation. But in this case, you still have to choose your, it still needs to choose your learning schedule, just like an SGD. But we also get to track our gradient. Instead of just forgetting about the gradient, we're incorporating it into something simple like Nesterov acceleration or acceleration. We're going to track our gradient, but we're going to track it specifically in the jth direction. And just try to get some sense of the magnitude of the gradient in the jth direction over, or by magnitude I mean the variance of the gradient in this jth direction over time, right? And so we're going to accumulate the variance of the gradient. The variance of the gradient. And then make the step size be inversely proportionate to this variance. Of course, more like a standard deviation. But this is step size in the jth direction. Right? In the jth direction, be inversely proportionate to 1 over root times this variance. Right? So the basic idea here is if the gradients are oscillating wildly, then we're going to have a high variance for those gradients. And then seeing this, we can modify our step size within that direction, within the jth direction, to be dampened somewhat. So this is really a more direct and slightly different approach than Nesterov's acceleration to adding some sort of a dampening that detects these oscillations. Now, a very popular optimizer just effectively combines all of these ideas. It's really not that innovative in a lot of ways. It just says, well, let's do all of the things. And that's Atom, which really just combines this Nesterov acceleration with RMS prop. Right. Okay. So all of these really are just different optimizers that you can create them, you can initialize them in TensorFlow, and then once you have them, you just have to feed them the appropriate gradients, and they are going to track either your acceleration term or these variances, whatever you need to be able to make these updates. And so I'm just going to talk about Adigrad and Atom at a high level, because really to use them in TensorFlow, you don't necessarily need to know their inner workings, although I would encourage you to look at those papers. Okay, so now our deep learning pipeline, the basic idea for a deep learning pipeline is first we need to specify our neural net architecture. So let's sort of recap. So this is all of the activation functions, all of the each layer, whether the layers are fully connected or maybe they are like LSTM layers or blocks, or maybe they are convolutional layers, and those are really specific to the application, the data set that we're talking about. So this we call all of these decisions the architecture. And then 2, using automatic differentiation, you create the computation graph. And now with TensorFlow 2.0, because it is run in eager mode, you don't create this computation graph and compile it first. You typically can compute and make the updates yourself in a sequential programming manner. Okay, so 3, you then evaluate the gradients. Right, these gradients. And then use these gradients in a SGD type solver. So use them in your optimizer, which will actually apply the gradients to the parameters. Now, one thing I'd like to mention also that made the deep learning sort of revolution possible is that a lot of these operations are very large tensor operations. So let's do star. And the tensor operations are ideally suited for GPUs, for graphical processing units. And that will make them, makes them run much faster than they would on CPUs. And so that's another thing that really enabled deep learning to work on with reasonable compute time. So all of those things combined make this deep learning pipeline possible. And it's really all of these different aspects acting in concert that make deep learning really a successful, viable strategy. So, for example, your architecture, it's very flexible because you can add and subtract pieces of a neural net architecture that suit your needs. You don't have to think about how you're going to do this back propagation. The automatic differentiation does it for you. And then the GPU will evaluate your gradients and make the gradient updates fast on the GPU. And then the optimizers, because they have just an excellent interface in these modern deep learning frameworks, they are going to also make those gradient updates in a sort of succinct way with minimal oversight. So that's it for sort of the conceptual part of the neural net lecture. We'll just finish off with a very quick modification to the iris data set and the iris pipeline, and just add a couple of layers to our already constructed linear neural net, or the simple 0-layer neural net. Okay, thank you.